Okay, thank you. It's a pleasure to speak to everyone this morning. And what I'm going to talk about, really a way of looking at different visions for how we handle hydrology. Because very often we have developed models over the years, we invested a lot of time in developing them, we get committed to them in strange ways, a Pygmalionistic approach perhaps, and then the danger is that we can defend them against advances in science. And we often shield our models through calibration. And calibration has great uses in hydrology, particularly when we're using streamflow measurements to look at large-scale routing and human interventions in the hydrological cycle. But in some of the physical processes, it doesn't have any place. And I would argue that, in fact, it's something that we need to fight in some way. It's the beast that we're not dealing with. And in fact, if you look at the history of other sciences, if astronomers in the Middle Ages had chosen to continue calibrating the view with the Earth as the center of the universe and the wheels within wheels of the planets going around, or had denied Kepler in the elliptical orbits and things like that, we would be in big trouble today. So anyway, I think hydrology, we have to move beyond mythology, stop calibrating it, and make sure we're clearly incorporating our scientific advances. And there's many wonderful examples of that, so that's good. But I'm also reflecting on the decade for PUB, Prediction in Ungauged Basins, which ended a couple of years ago. And at the beginning of PUB, in a wildly idealistic time, we said, well, over 10 years, let's improve existing models, but eventually we'll move away from that and their calibration and move towards developing new innovative models that wouldn't calibrate but would predict based on scientific understanding and new technologies that are available, such as new satellite information. LIDAR was developing, subsurface surveys, things like this, which are becoming available. And much of that technology for measuring the basin has become available in wonderful, wonderful ways. And we have atmospheric models now, which are getting down to scales of kilometers or less with reasonable predictive capability. So this should start to work. And however, Hubert Safinger, who's a brilliant scientist and the last chair of the PUB decade, wrote in his article in 2009 that no matter how physically based a model is, parameters will always be effective, and essentially we always have to calibrate. And so I'm going to argue that no, let's keep back to that idealistic idea and keep moving towards reducing calibration. Maybe it doesn't get completely eliminated, but we keep pushing it into the corner. So why do we calibrate? Well, sometimes we calibrate because our models are simply wrong. They have inappropriate ideas within them. And so I coined the term hydromythology that Al talked about. These are concepts that keep persisting in models. And some of these are in the Canadian context where we have basins that were glaciated fairly recently, and a lot of typical temperate zone hydrology doesn't work for us. And so some of these ideas, so for instance, temperature index, that we can use that to extrapolate snowmelt estimation. No, you can calibrate temperature index at a point pretty well, but you can't move it 10 feet without it failing. And you certainly shouldn't be using it with a climate impact model. That we use potential evapotranspiration to estimate actual evapotranspiration. In fact, they behave in exactly opposite ways in dry environments. And it's one of the worst things you might want to use. Address actual evaporation directly. A third one, that we can't use radiation inputs to our models because if we haven't measured it, well, we can't possibly estimate it. Well, in fact, that's not true. And there are lots of very clever and useful ways to estimate long and shortwave radiation from temperature, humidity, your location, slope and aspect, things like this. That snowpack forms directly from snowfall and accumulates nicely on the ground without redistribution and sublimation by wind via blowing snow or interception, sublimation and melt out of the canopy. We can develop that concept if we look at the wonderful snowtail network, which are all in forest clearings where there's no redistribution and there are no canopies right over our snow pillows. So in fact, that works in those clearings and nowhere else in our basins. And so that's one that has fooled many people, and that's one I'm going to really address quite strongly in this talk. That we can address soil infiltration without macropores. Try applying green amp over a large basin with the real soil properties in it. It doesn't work. It works in a lab in a column. And of course we have to include macropores. It's not a scaling problem, it's a lack of process problem. Or that all portions of the drainage basin contribute runoff to the stream. Stacy Demansky's talk showed a basin where maybe 3 to 4% contributed to stream flow, jumping up to 80-90% as the farmers drain the fields. You get incredible changes in the hydrology. It's really important mechanism that we forget. Frozen soils behave like unfrozen soils. We've learned in Canada the hard way you can't assume that. And that base flow is only determined from subsurface water. Well, there's surface components to it as well. So I'll jump into more meat here, the Saskatchewan system, a place where we might test this. So in Western Canada, the headwaters of the Saskatchewan River system feed our largest irrigation area and some of our largest cities, Calgary, Edmonton, Saskatoon, Regina, and lots of hydroelectricity further on in Manitoba. It was recognized early on by Church that this is going to be a challenging place to work because of the complex snow processes occurring in that environment. So we instrumented a catchment in there about 11 years ago and started developing a hydrological model that might help us to address it. And it's really a platform for assembling these things. We call it the CRIM platform. So it's object-oriented. You bring in modules as you need them. There's lots of options at different levels of complexity based on the data and the way that you want to model. You can stop at evapotranspiration. You could stop at snowmelt or go right through to groundwater and stream flow. And so there's a range of conceptual and physically based modules that you can include in there. And so it's a very easy way to do some falsification of testing, which is essentially what I'm going to show you. So the Hillslope hydrology essentially looks like this. We allow surface-subsurface drainage. There's some macropore flow. We have up in the watershed, we have redistribution of snow, forest canopy effects, things like that. They're all available to it. Pretty standard stuff. Alpine snowmelt, one of the snowmelt model options is Snowbow, developed by Danny Marks and colleagues. And I think a lot of people are very familiar with that here. So it's reasonably physically based model for this kind of application. Now, we can set up a structure with the CRIM platform, and this is what we created, taking radiation observations. We estimate long wave, short wave to slopes. I'm going to cut out these two modules in here, but I'll explain what they do before we get rid of them. Canopy deals with snow interception and sublimation in the canopy. It deals with drip out of the canopy, interception of rainfall and evaporation of rainfall from the canopy, and also the reduced shortwave radiation and enhanced long-wave radiation out of the canopy, as well as reduced turbulent transfer out of the canopy. So it's going to have important effects in a forested basin. And PBSM is a derivation of the prairie blowing snow model. It's been modified a bit for application in this environment, but essentially allows us to redistribute snow between landscape units in the Alpine area. So I'm going to take out those two, and we're simply going to run this as a snowmelt model with albedo decay, with net radiation for the summer, evapotranspiration, infiltration, and then finally to Muskingum routing to get the water out of the basin. So here's Marmac Creek. It's been operating since 1962, off and on, but it's been revived over the last 10 years and heavily instrumented right now. And you can see it has alpine environments, forested environments, experimental clear cuts going back to Swanson and Golding's work in the 70s and 80s, and groundwater observation wells and a network of stream gauges. So good place to work. Up at the top, Mount Allen Cirque. This is near the Olympic site in 1988. But it's a very snowy place. Snow hangs on well into June in that environment. Okay, so working out the hydrological response units, the things that we've taken into account are elevation bands, slope and aspect, and forest cover, but remember, I'm not going to use forest cover in the first iteration of the model here. But we also have soil surveys for the basin. We have a lot of groundwater exploration for the basin to work this out. When you go into the parameterization, again, using the wealth of studies in the basin over 50 years, we have a lot of information to set hydraulic conductivities, the stream flow routing parameters, the soil parameters, and the vegetation. We've had LIDAR, we've had snow on, snow off LIDAR as far back as 2007. So there's lots that we can work in for model parameterization that we shouldn't need to calibrate from this, and I won't in the example I'll show you. So let's try it, what we'll call CRIM no redistribution. So there's no forest canopy, there's no blowing snow. So how do we do in the Alpine? Well, this is a north-facing slope that normally scours, and you can see the snow surveys here, and the black is cumulative snowfall over the winter, and so a lot of it blows away, and the model doesn't show it blowing away, so it stinks. The root mean square difference, 236 millimeters, and mean bias of 2.55. That's terrible. If you look at the south-facing slope, which is normally where the drift forms, and you can see we get more snow than we have snowfall in some years, and the model is not able to predict that. It's predicting the same thing as on the other face, and again, it stinks. So now we have a mean bias of minus 0.48, and a root mean square difference around 260 millimeters. Not very good. We go down to the forested area and look at a forest and a clearing, and in the mature spruce forest, again, it's not great. Mean bias is still 0.62. There's lots of snow interception in this forest. We figure we're losing 60% of the annual snowfall to sublimation losses in this, and of course we cut that out of the model so it doesn't model it. In the forest clearing, which would be like a snow-tail site in the United States, the model works really well because we're not redistributing anything, and it's just falling and sitting in the clearing, and then it melts in the spring. And snowmelt is a good snowmelt model, and it does a great job. So very, very good. Okay, how about the hydrographs? How well can we do with the hydrographs? And this is without any calibration of the parameters. And it's not terrible, but it's there's a Nash sucklift of 0.22, root mean square difference of 0.2 cubic meters per second, and there's bias of almost 10%. And if we look at the, in different years, how well we do with the summer discharge, the seasonal discharge, and the peak daily, it's fair. Sometimes we're up, sometimes we're down. So you'd want to do better than that. So we're not going to calibrate at this point. This is the point where often as hydrologists we go in and we calibrate. We're not going to do it. We're going to change the model. So I'm saying, do we stop the bullet or we dodge the bullet? In this case, we're going to stop the bullet, and we're not going to do that. So, okay, that's bad. So, okay, so what do we do? Well, you go back to clever grad students of the past. One was Matt McDonald, who worked out a way to redistribute blowing snow in the Alpine using a hydrological response unit concept. You saw it in Al Petronero's presentation, where he's referring to redistribution between tiles and mesh. Same idea. And so we can blow snow over the ridgetop and put it in the forest and the drifts where it belongs. Then another one, Chad Ellis, another wonderful student working on the forest canopy effects, snow interception, sublimation, subcanopy melt, impacts, drip, and all that. And so we'll add those components into the model. The interception goes back to the work of Noel Hedstrom in the 1990s. And we'll try it again. So now it's working pretty well. We can get the Alpine snow water equivalent reasonably well. We can get the south-facing slope snow water equivalent reasonably well. Root mean square differences have dropped dramatically. And we can now get the forest reasonably well. Actually, we do slightly less well in the clearing. It's interesting, but that's science. But the mean bias is small at these other sites. And when you look at the hydrographs, we're doing much better. We're up to a 0.58 for Nash Sutcliffe. That's probably kind of respectable without calibration. And yes, we could do a better job with calibration, but we're not going to, because this is a scientific demonstration. That tells us we still don't know everything. We still have work to do in the watershed. So the improvement in prediction from these things, big drop in the root mean square differences, big drop in the mean biases, increase in the Nash Sutcliffe as we go down into the stream flow end. So we can fight hydromythology. We can beat calibration. There are alternatives to that. We don't have to do that. And in fact, we can still be respectable predictors without those methods. And so a few conclusions: that if we have a better understanding of our snow processes, that can be the basis for better modeling, better prediction. If we take in all the wonderful advances in remote sensing, field studies, and other things available, bring them into our models, embrace them, we can do a better job. And a lot of neglected algorithms might improve things. So a lot of this was discussed in a paper published in Hydrology Intersystem Sciences last year by Fang et al. So thank you.
We have time for one quick question. Jim?
Very nice talk. Very much in your reductionist camp, striving to reduce calibration. But aren't your concepts of hydrologic response units and parameterization just the first guess and the first of calibration, and maybe by just accepting those, perhaps accepting the mythology in sight, you believe your first guesses?
Well, the hydrological response units were chosen based on the processes operating in the watershed and based on the understanding. So I'm not arguing that everything should be reductionist. In fact, what I argue is that reductionism is important, but in fact you also have to have deductive approaches, and you have to have abductive approaches, which is where we take science in sideways from other places that we're familiar with and move them into basins that we don't understand so much. So in fact, I would argue it's a three-point approach to it: deduction, induction, and abduction. But that's philosophy, and it's probably mostly nonsense. So.